The fifth generation of wireless communication rapidly approaches prevalence. Infrastructure and technology must change to facilitate this. It is vital that in this period of development, realistic simulations are widely accessible. Part of the physical layer of the 5G stack is forward error correction. Errors can be introduced in a signal when it is sent through noisy channels or difficult to navigate environments. Here we are transmitting data from this antenna. This data is encoded using low density parity check or LDPC codes as a means of forward error correction. This is the 5G standard for the user data channels. LDPC encoding handles forward error correction by selecting many random groups of bits from a transmission to be paired with a single parity check bit. This makes handling errors in transmission simpler than assigning large groups of bits to just one parity bit. This parity check bit is then used by the LDPC decoder to ensure that all the data is correct. With the cooperation of Xilinx and the University of Strathclyde, we have developed a web application solution for benchmarking LDPC encoding and decoding in realistic transmission environments. The metric for evaluating forward error correction is bit error rate. This can be analysed over a range of SNR values. SNR values determine the signal strength. Our developed solution functions both on the ZCU111 Xilinx Field Programmable Gate Array, or FPGA, and Amazon's recently released Elastic Cloud Compute F1 Cloud FPGA instances. We've also created a multipath interference model to better simulate the noise that can occur in the real world. This is our FPGA design. Random data is generated before going through the LDPC encoder, after which errors are introduced in the data through a channel model before being decoded. This allows the performance of LDPC forward error correction in the system to be evaluated. Our application is available as an Amazon machine image, which packages up the solution for users so that all they have to do is select our AMI at the startup of their F1 instance. We're now going to go through this process and then run some example simulations to compare error rates. The application operates based on input being passed down through drivers to communicate with the FPGA. The FPGA then provides the results to be output. Our web application facilitates this input handling and presentation of results. It was developed in Jupyter Notebook for its modularity and prevalence within the science and engineering fields. And here's the user interface. It displays the power consumption of the board, stats for ongoing runs, and graphs to display results. We're now going to configure a run. We can select the LDPC code type. The user can also add their own custom code types, channel model and modulation type, maximum iterations, and whether the run should terminate early or not. The SNR sweep can also be defined along with some other run determining characteristics. We're now going to begin the run. We would expect to see the error rate decrease as the SNR increases. Our application also has the capability to evaluate the latencies of the encoder and decoder blocks at particular SNR values. So we can see the bit error rate, block error rate, and average iterations all over the SNR values that we defined in our sweep. Tools like ours are going to be of crucial importance as more and more people require inexpensive solutions to simulating and evaluating LDPC codes for 5G communication.